Okay, so yeah, um, we took a 2 week break from this because of my conferences and everything. So let's resume today. So Harshal, you had asked me like how to represent like a reaction, the change in reaction. How do you express it with the change in temperature and pressure, right? Or can you just post the question again on the chat wheel just to be sure? Okay. Show mathematically temperature and pressure affecting the rate of reaction. Okay, fine. We'll do that. So how does slide show correct? Okay. So how does temperature and pressure affect the rate of reaction? Fine. Let's take a very simple example itself and we'll see how we can see. So A to B, a very simple, straightforward first order reaction. So first order reaction, and you can write the rate minus RA as KCA. So you're following, right, Harshal? Okay. So minus RA is equal to KCA. Now this K you can write it as K0 e raised to minus E by RT into CA, right? So from this you have the temperature term. So now if you vary this temperature, your rate constant will change. And if your rate constant changes, your reaction rate will also change, right? So now we just showed how temperature affects the rate of reaction. Now how does the pressure affect this rate of reaction? The same thing, you know, we have this rate as minus RA is equal to minus KCA. Now assume this is a gaseous system or a gaseous reaction. So for gaseous reactions, you have this ideal gas laws, right? So PV is equal to nRT. So if you take this V this side, we'll have P is equal to N by V into RT, and this N by V is what? Concentration C. C into RT. Right? Now you can extend this to partial pressures as well. So PA is the partial pressure of A, and that will be equal to Ca, which is the concentration of A into RT, right? So from this, you can write Ca is equal to what? Pa by RT. Okay, so just substitute this Ca here. So minus Ra will be what? K into Ca, and Ca is Pa by RT. So now you have both the pressure term as well as temperature term, right? So that means what? If you vary the pressure, or if you vary the temperature, or if you vary both, this reaction rate will change with respect to whatever the variation that is occurring for pressure and temperature. So this is how you can represent mathematically how reaction rate varies with temperature and pressure. Understood? For nth order, pretty much the same thing, what will be the nth order reaction? Let's say Ra is equal to K Ca raised to N. So this Ca, you just write it as K into Pa by RT, the whole raised to N. That's all. Right? So if you have a reaction like this, say, minus Ra is equal to K Ca into Cb, you can also write it Ca, we'll take the general case, Ca raised to N, Cb raised to M. Let's say this is some, pth order reaction. Whatever the order is, whatever N, M, whatever it is, we can write this as, K into Ca, which is, Pa by RT, the whole raised to N, and Cb, you write it as Pb by RT, the whole raised to M, right? So you can represent any order reaction like this, but the assumption here is that it is a gaseous reaction. Only for gaseous reactions, you can represent, your concentration in terms of, partial pressures. For gas reactions, you can do this. For liquid and solid reactions, you can't do this. So so I'm not sure how we can, find the pressure variation for, reaction rate for liquid and solid reactions. But for gaseous reactions, this is how you do it. Fine. If this is clear, we can move on. Shall we move on? Okay, fine. So last class we were looking into catalysis, right? We just started the very basics of catalysis. So we saw, how what all different steps are there in a catalytic reaction. The 7 different steps in a catalytic reaction, and we imagined 3 scenarios. So the first scenario is where both the diffusion steps, the internal and external diffusion steps, are very fast. That means any of, adsorption, surface reaction, or desorption can be rate determining. And then there was scenario 2, where external diffusion is determining, and the other steps are very fast. And the scenario 3 is where internal diffusion can be rate limiting, and the other steps are very fast. And we looked at how we can write the rate of reaction equations when adsorption was rate limiting, right? So we took this scenario 1, and we looked into a very basic example, A giving B with S as the vacant side. We saw how, what all ways S can get, I mean, the reactants can get adsorbed on the catalyst active side, and we wrote a lot of, equations and so on. So we'll start with the continuation of this. So what we have to do is, you know, basically pretty similar to what we did last class. So we have these, 5 different steps: internal diffusion. Oh, sorry, it starts with external diffusion, right? Yeah. So external diffusion, then comes internal diffusion, then comes, surface reaction. Okay, I'm missing steps here. Then comes adsorption, then comes surface reaction, then comes, desorption, then again, internal diffusion happens, and then, external diffusion happens. So that's how these 7 steps occurs in a catalytic reaction. So we majorly focused on adsorption being the rate determining last class. So as I said, the adsorption can be single site adsorption or dual site adsorption, and we looked into how we can write the different equations for all these different types of adsorption that can happen. So now what I'll do is I'll do the same, but for surface reaction and desorption being the rate limiting steps, and I'll try to keep it brief as possible. So, according to schedule, actually, we are supposed to finish no, chemical reaction engineering by last class itself. But since we had to cancel 2 classes, I'll try to finish this catalysis part today itself. So I'll just brief through all these concepts, and we'll also try to do 1 or 2 problems. So, anyways. So we'll start with the surface reaction. So surface reaction, it can also be of 3 uh, different kinds of reaction that can happen. Single site reaction model, dual site reaction model, or there is a special case called LA radial model. Okay, so in single site, so if we take an example of the reaction A giving B, then the steps will be what? A will first get adsorbed to a vacant site. Let's represent vacant site as V, and will become AV, which is the activated complex. Then this activated complex AB will react to form the product BV. Then this BV will get desorbed to form B plus vacant site B, right? And this is our reaction step. So this reaction, a single site model, what it says is, so if we have, let's say these are the active sites, then A will come, A will get adsorbed here, and it will form, AV, and this will react, and B will also form on the same active site, and then it will get desorbed and so on. So basically, this is a single site mechanism. Now, a dual site mechanism. Okay, we have to write the equation also for this, right? So AV reversibly giving BV, then the rate of reaction will be K1 CAV minus K minus 1 CBV, right? So K1 K minus 1. So this will be the overall rate of reaction for this reversible reaction step, right? Now if we do the same for a dual site mechanism, so in a dual site, let's take the example, A plus B giving C plus D. So what happens is, let's assume both A and B are getting adsorbed. So I'm not going to write the adsorption steps. I'll just directly write the reaction step. A will get adsorbed to a vacant site to form AV, and B will also get adsorbed with the vacant site to form BV, and this will react in a reversible manner to give CV and DV. So if we have active sites like this, so A will be adsorbed on this, B will be adsorbed on this, and this will undergo reaction, and you will get C and D, which are also adsorbed on the active sites. Then later this C and D will desorb from the active site, and it will just go into the bulk. So if we write an overall equation for this, R reaction, it will be, so K1 and K minus 1. So K1 C into CAV and CBV minus K minus 1 CCV CDV. So this will be your overall rate of reaction for this. Now the special case was LA radial. So LA radial also pretty much, you can take the same reaction here, A plus B giving, we'll just take one product C to avoid complication. So you have A plus B giving C. Only one of these reactants will get adsorbed. Okay, let's assume A is the one that is getting adsorbed. That means B won't get adsorbed. So the adsorption and reaction will be happening like this. So you have vacant sites. A will get adsorbed, but B will stay in the bulk itself. It won't get adsorbed. And, and this will reversibly react and it will give you the product. Now the product can either be adsorbed on the active site, or it can also be you know formed separately from the active site. That depends on each and every individual cases. So this is a special type of reaction that happens in catalysis, and that is called as an LA radial mechanism or model. Okay, so if we write the overall rate of reaction for this, rate of reaction will be K, again K1 and K minus 1. So K1 C into AV, because A is the only thing that is getting adsorbed, and CB minus K minus 1 C CV. Or this can also be just CC, depending on whether the your product is getting absorbed or not. But also one more thing that you should notice, as I just said, you know if you assume these are in gaseous phase, or these reactions are gaseous in nature, you can write this rate of reaction as K1 CAV into PB, which is the partial pressure of B, minus K minus 1 CCV. Right, so this C will become PB, partial pressure of B. Right, okay. So this is just the brief equations for surface reactions, and pretty much the same thing you can apply for desorption steps as well. So if you have let's say the same A giving B, the steps will be A getting adsorbed to form AV. This AV will react to form BV. Then BV will desorb to form B plus V. So this is your desorption step, right? And desorption is pretty much the same thing. You can write the rate of desorption as let's say this is K1 and reversible is K minus 1. K1 CBV minus K minus 1 CB into C. So this is pretty much the set of equations that you need to conjure up when you are trying to solve a catalysis reaction. Now there is something called as a Langmuir-Henselwood approach. So that is what you will be doing with all these reactions that you just conjured up. So if you are given a system, let's say A giving B, you can write all these various steps. Adsorption will be A plus B giving AV, and then the reaction will be AV giving BV, and the desorption step will be BV reversibly giving B plus V, right? So based on different conditions and different questions, any one of these can be rate determining step. So that is where we will be using this Langmuir-Henselwood approach. So in this Langmuir-Henselwood approach, the first step is to assume a sequence of mechanism. So this is our sequence of mechanism that we did for this simple reaction A giving B, which is A getting adsorbed on a vacant active site, and A on the vacant active site, which is basically an activated complex. It will undergo reaction and reversibly give the product, which is also an activated complex. That means the product is also like adsorbed on the active site. Then the product from the active site will get desorbed to give the product and a vacant site. So this is our sequence of mechanism for most of the general cases. Okay. Now the second step is write the rate of each step, assuming it is reversible. Oh, that is also what we just did. So we the first step is we had to assume three steps, which is adsorption. So this is adsorption, then the surface reaction, and then the diffusion. Desorption. So we assumed the sequence of these three steps. We wrote the reaction rate equation for it. So you can write the rate equation for adsorption. So here this adsorption will be, my R adsorption is equal to K1 CACB minus K minus 1 CAB, right? Then the reaction will be K1 CAB minus K minus 1 CBV. Now we will write it as K2 to avoid confusion. And this desorption R desorption will be K3 CBV minus K CB K3 CB. So you can write these three rate of reactions based on these three elementary steps that you assume. So that is step number 2. And the step number 3 is assume one of these steps to be rate determining. So you can assume any of these to be rate determining. In most of the cases for your gate exams, it will be given which is the rate determining step. So you usually don't have to assume anything, but the Langmuir-Henselwood approach is like this. So you assume one of these to be rate determining, and continue with the fourth step, which is formulate the overall rate law. And we have to replace all the terms like CV. So how we replace it, we'll see in with an example question. But anyways, so what we have to do as the fourth step is after assuming one of these steps to be rate determining, we just try to formulate the rate law by replacing one of the not one of the by replacing all the CV terms or concentration of vacant site terms. Okay, and from this, yeah, from this 4 steps, you can find the rate law, and you can even find the relation between rate and pressure. So as I said, if you have these terms CA, CB, and so on, you can write it as PA, PB, which are the partial pressures of A and B. And by using these, approach, you can find a relation between the rate and the pressure of the system. And the final step is to just compare it with the raw data. So usually the last step is not required when it comes to questions specifically from GATE. You might not need to bother about that much, but the approach is pretty much same for any case. So first you assume a set of steps, then you try to write the rate equations for each of these steps, assuming they are reversible. Then assume one of these steps to be rate determining, and using that try to formulate a rate law, overall rate law, and thus using this rate law you try to find a relation between the rate of reaction and pressure, and then compare it with the data that you have. So this is the Langmuir-Henselwood approach. And also in the last class I have mentioned, so here you had adsorption, reaction, and desorption as the three possible steps that can be rate determining, because you said that diffusion is very fast and they can't be rate determining, right? So let's say adsorption is rate determining. That means the rate of reaction and rate of desorption can be taken as 0. So taking these two as 0, you find the terms corresponding to CAV, CBV, and so on, and CV also. And to find CV, you take the total side balance. The total side balance will be C total is equal to CAV plus CBV plus C vacant. Now this is just for this very simple reaction A giving B, right? So this will be the side balance for that. And let's say if you have something like an inert as well with A, and inert is also getting adsorbed like this. So I plus V giving IV. So if it is also getting adsorbed, then you will have a term CI as well. Sorry, IV. Okay. So this is the total side balance. And using all this, you can find the overall rate law. So you can find the values for CV and all the CAV, CBV terms from these two conditions, which is the rate equal to 0 and the side balance. So equation 1 and equation 2. So use D2 to find or eliminate the terms CV, CAV, CBV, and so on, and then substitute everything in rate of adsorption. Okay, because rate of adsorption is not equal to 0 because it is rate determining. So that is where you have to substitute all these values, and finally you will find the overall rate. Okay, fine. So this is basically the brunt of scenario 1, where any of adsorption, desorption, and reaction can be rate limiting. Now scenario 2 is where external diffusion can also be rate limiting. So it is either in scenario 2 you can have either external diffusion as the rate limiting or the reaction as the rate limiting. Everything else, adsorption, desorption, and internal diffusion, these are not rate limiting and you can take their rate as 0. So this is scenario 2. Okay, so I'll I'll give a brief introduction to scenario 2 as well anyways. So assume you have a particle like this or a catalyst, let's say. So on the surface the concentration of A is CAS. Okay, so this is the bulk of A, and let's say this is Ca, and you know there is a fluid that is flowing like this. So basically in this scenario too, what happens is both reaction kinetics and mass transfer that is placing taking place. So reaction kinetics is where the surface reaction can be rate limiting. Mass transfer basically external diffusion. Okay, so rate per unit area, rate per unit area. Let's take it as R1. This is basically what RA by area. So what is the unit of RA? Mole per meter cube second. This is divided by meter square. So that is basically what mole per meter second. And this is basically flux Na. Okay. And by Fick's law or mass transfer basically, we must have learnt about this. Flux Na is equal to Kc into Cab minus Cas. So Cab is this. So this is according to your mass transfer. Now according to your um, kinetics, Ra is equal to Kca, right? And if we somehow take something like R1 is equal to K double dash Ca. So as I said, this R1 is basically, Ra by area. So rate of reaction per unit area. And this will be K dash into Ca. And this K dash is the modified, rate constant. K by area, let's say. Okay. So, yeah. So now R overall will be K double dash into CAS, which is the concentration of A on the surface. So this R overall is basically equal to R1 or this rate. Okay. Yeah, this is CAS, sorry. And this is equal to Na. So basically, just a lot of mathematical manipulation and so on. Basically, what it comes down is K double dash into CAS will be Kc into Cab minus CAS, because R1 is equal to Na. So from this we can find a term for CAS, right? So CAS will be equal to Kc into Cab by K double dash plus Kc. And now we just said R overall, or the overall rate of reaction, is basically R1, and that is K double dash into CAS. And this K double dash CAS, just substitute it for CAS, K double dash Kc Cab by K double dash plus Kc. just divide this K double dash KC in the denominator, you will get CAB by 1 by KC plus 1 by K double dash. Now this 1 by Kc is called as mass transfer resistance, or basically this is the resistance to diffusion, resistance of diffusion, and this is resistance of reaction. Okay, so we can have three different cases. Case 1, where Kc is very much greater than K double dash. So that means resistance of this diffusion is very less than resistance of reaction. Okay, so that means what? Resistance of diffusion is less means diffusion will happen very fast. Diffusion will occur very fast and reaction will be occurring very slow. So what does that mean? Reaction is rate determining because it is the slower step out of the two, right? This is just substituting these different cases on this equation CAB by 1 by KC plus 1 by K double dash. Now you can have the other two cases as well. The case 2 is K double dash very much greater than KC. That is the, yeah. So that means R diffusion is very much greater than R reaction. Or here reaction will happen very fast and diffusion will happen very slow, and this will be rate determining. And case 3 is where K double dash is equal to Kc. So both are in equal values, and that means both these reactions have control over the reaction. So both external diffusion and surface reaction have control. So this is also called as intermediate control. Okay, yeah. So basically this is the gist of the scenario 2, where external diffusion can also be part of controlling the rate. So what we'll do is we'll stop the concepts here. I think we might need one more class for completing the remaining portion. Okay, fine. So anyways, what we'll do is we'll stop the uh, concepts for this, and we'll try to solve one problem, because I think it's almost 6:45 now. So I think if we try to solve one problem, then if we have time we can look into the other concepts as well. So the remaining concepts are only this scenario 3, which is basically where internal diffusion can also be rate limiting, and inside this only you have a value called as delay modulus and effectiveness factor. right? So yeah, this is for the scenario 3, and after this there is one small portion called catalyst deactivation. So with these two portions, CRE will be more or less complete. We must have covered all the portions in CRE. Um, what we'll do is we'll do one problem now, and if time permits, we'll look into these two concepts as well and see if we can squeeze in one more problem with regards to delay modulus and effectiveness factor. Right. So let's move on to problems. But before that, yeah, I know this is, I'm just rushing through these concepts, but I hope it is clear to both of you. If you have any doubts, just please ask me. I am okay to like repeat all these things again, so it's fine. So everything clear so far? Okay, fine. Then let's move on to a problem. Yeah. Just go through this question. We'll see. So this is based on this radial mechanism that I just went through a few minutes ago. So this is also this is a catalytic question. So basically, a vapor phase catalytic reaction happens, and they are asking us to find the overall rate of reaction in terms of total pressure PT. So let's see how we can solve this. Okay. There's a question from GATE 2014 from Chemical Engineering, question number 38. A vapor phase catalytic reaction Q plus R giving S follows radial mechanism where R and S are not adsorbed. Initially, the mixture contains only the reactants in equimolar ratio. The surface reaction step is rate controlling. With constants A and B, the initial rate of reaction minus RO in terms of total pressure PT is given by dash, and the four options are given as here. So this is a question from catalysis part in chemical reaction engineering, and the reference NPTEL lecture can be found in lecture 2, steps in catalytic reaction, adsorption, desorption and reaction, chemical reaction engineering 2 by Professor Sanjay M. Mahajani, Professor Ganesh A. Vishwanathan, Professor A. K. Suresh from Department of Chemical Engineering, IIT Bombay. So here the reaction given to us is in vapor phase, and that is Q plus R giving S. And this follows LA radial mechanism. And in the question, they have mentioned that only Q is getting adsorbed. R and S are not getting adsorbed. So based on this, we'll try to formulate the different steps in the reaction and their corresponding rates according to Langmuir-Henselwood approach. So here Q plus R giving S is our overall reaction, and Q is the only thing that is getting adsorbed. So the adsorption step will be Q plus V reversibly giving QV, where V is the vacant site, vacant active site. Then the reaction step will be QV plus R giving S plus V. Since the product is already in a desorbed state, there is no desorption step. So there are only two steps here. Step number 1, which is the adsorption step, and step number 2, which is the reaction step. So we can write the corresponding rate equations as well. So if we write, rate of adsorption, it will be, let's take it as Ka and K minus A as the rate constants for this adsorption step, and the reaction, let us take it as Kb and K minus B. So for the rate of adsorption, the overall rate of adsorption can be written as Ka into Cq Cv minus K minus A Cqv, and the rate of reaction can be written as Kb Cqv Cr minus K minus B Cs Cb. Now the concentrations of CQ, CR and CS, it can be written in terms of their partial pressures as well. So if we write the reaction rates in terms of partial pressure, we can write rate of adsorption as Ka PQ CV minus K minus A CQV, and rate of reaction as KB PR CQV minus K minus B PS CV. Okay, so let us take this as equation 1 and equation 2. Now, one more equation we can write, the total site balance. This will be CT, that is equal to CV, the vacant site concentration, plus CQV, which is the concentration of the adsorbed reactant Q, or the concentration of the activated active sites. So let's take it as equation 3. Now, here it is mentioned that reaction is rate determinant. So that means we can take rate of adsorption as 0. So that means Ka PQ CV minus K minus A CQV is equal to 0. So from this we can write the equation in terms of CQV as CQV is equal to Ka by K minus A PQ into CV. Now this Ka by K minus A will give you the equilibrium constant Ka, because Ka is the forward rate constant and the K minus A is the backward reaction rate constant, and the ratio of the forward to the backward reaction rate constant will give you the equilibrium constant capital Ka. So CQV can be written as capital Ka PQ into CV. Now what we can do is we can find the term for CV by using the side balance. So from equation 3, the side balance CT will be CV plus CQV. And we can substitute for CQV as CV plus Ka into PQ CV. So from this, if we rearrange, we can write the term CV separately. So CT will be CV into 1 plus Ka PQ, or CV will be equal to CT by 1 plus Ka PQ. So let's take this as equation 4 and this as equation 5. Now we will substitute these values for CQV and CV in our rate determining step, which is our reaction rate. So our reaction is will be the rate determining step, so that will be R overall, and that will be equal to Kb PR CQV minus K minus B PS CV. So substituting for CQV and CV, we get Harshal, your mic is unmuted. Okay. Okay. So yeah. So what we'll do is we'll substitute CQV and CV in this equation. So R overall will be Kb PR into CQV, and CQV is CT. Oh, sorry. So R overall will be equal to Kb PR CQV minus K minus B PS into CV, and that we substitute for CQV and CV, will get Kb PR CQV is Ka PQ and CV minus K minus B PS into CV, and CV will be CT by 1 plus Ka into PQ. Now we substitute this CV here as well. So we'll have Kb PR Ka PQ into CV, that is CT by 1 plus Ka PQ minus K minus B into PS CT by 1 plus Ka PQ. So we can take these two terms out. So CT by 1 plus Ka PQ into Kb into Ka PR PQ minus K minus B to PS. So this will be our overall reaction rate. Now they said that initially only the feedstocks are present or the reactants are present. So initially only Q and R are present. That means S is 0 initially. So if we write overall reaction rate at initial stages R0, then here PS will be equal to 0. So in our overall reaction rate at initial stages at T equal to 0, this PS term will get cancelled. So our new reaction rate at the initial time T equal to 0 will become minus R0 equal to KB, KA, PR, PQ, CT by 1 plus KA, PQ. Now if we take KB into KA to CT as a constant A and KA as B, we'll get this initial rate as minus R0 is equal to A into PR PQ by 1 plus B PQ. Okay. So now, since they have given in the question that R and Q are equimolar in the system. So that means we can take PR equal to PQ and that will be equal to the pressure PT. So what we can do is we can substitute PT in terms of PR and PQ and we'll get our initial rate minus R0 as A into PR into PQ, which is PT into PT, that is PT square by 1 plus B into PQ, and PQ will be PT, so B into PT. So our initial rate equation will become minus R0 equal to A into PT square by 1 plus B into PT. Now this is our required initial rate and this is the same as the option C given in the question. So our required answer here is option C, minus R0 equal to A into PT square by 1 plus B into PT. So that is our initial rate of reaction in terms of total pressure for this given question. Is this clear? Yeah. So basically what we did here, this is pretty much the same concepts that we were applying, for the last few slides, we are seeing how to write the equations and everything, right? So this is how you apply it. So you do this in the Langmuir-Henselwood way. You assume the different steps for the given system. Here the different steps are only adsorption and reaction, because they said that desorption does not happen here because S is not getting adsorbed. So the product that is forming is already in the desorbed state. So there is no desorption step here. So based on the system that you are trying to solve, you assume a series of steps, for the system, and you write the reaction rate equations for these steps, assuming that they are reversible in nature. And when you do that, you take one of those steps as the rate determining. Here in this question, they have given that the reaction step is the rate controlling step. So that means the adsorption step, the rate of adsorption can be taken as 0. So we took that as 0, and using that we found a term for CV and the adsorbed reactant CQV, and we eliminated these terms CV and CQV from our main overall reaction rate equation. And the overall reaction rate equation here is basically the rate equation for the surface reaction step. So that is basically our aim in these questions. So whatever is our rate determining step. So wait. Um, so whatever is our rate determining step. So that rate of this rate determining step will be the overall reaction rate, and that is not equal to 0. But everything else, you can take the rate equal to 0. So in the last question, the surface reaction step was a rate determining step. So that reaction rate is not equal to 0, and that reaction rate is the overall reaction rate for that system. So whatever was the remaining steps, the adsorption was the remaining step in that last question. So rate of adsorption, you can take it as 0. And using this concept that, whatever is not the rate determining step, you can take their rates as 0. And also you take the side balance. CT is equal to, CAV plus CBV plus so on plus C vacant. So using these two concepts, that the rate of non-rate determining steps as 0 and the side balance CT equal to so and so, you find terms for CV, CAV, CBV and so on, and you eliminate these terms from your overall reaction rate. So that is basically the objective of these sorts of questions when they are asked in this manner, right? So for that only we are writing all those reversible reactions and their rate equations, and doing all these mathematical manipulations. So our basic aim is to just eliminate these terms from overall reaction rate. And after eliminating, whatever term you are getting will be your overall reaction rate. So that is basically the aim of this last question, right? Okay, fine then. We'll stop here. But as I said, we still need to, look into our scenario 3, which is the internal diffusion. And by internal diffusion, the major focus of that is the Thiele modulus. So Thiele modulus will be the major focus, and the effectiveness factor. We'll try to solve a couple of questions also based on this Thiele modulus and effective factor. And once that is done, a very small topic is left, which is the deactivation of catalyst. So these two portions are remaining in CRE. We'll try to cover these two portions tomorrow in the next class, I mean, which is the coming next Monday. And we'll try to solve, 2 or 3 problems as well based on this internal diffusion, and also, maybe if possible, we'll look into one more problem based on this the scenario 1 and scenario 2. So I'll see if we can get any such problems. And with that, I think we can conclude CRE. And after CRE, I want to start mechanical operations. So if everything goes well, we can start mechanical operations by the start of January. Or if things go very well, we can give a brief introduction of mechanical operation during the next class itself. Right. So yeah, that's it for today. Thank you for joining, and I'll see you all next class.